Welcome to the flock. Let's dive into nuclear chemistry, exploring the concepts of nuclear fusion and fission, along with alpha, beta, gamma, and neutron radiation. Stick around to see how you can solve for nuclear decay problems just like these. Now, when you think of nuclear chemistry, the first thing that comes to your mind is probably a nuclear explosion, mushroom cloud, or something like this: caution signs, danger, radiation. While nuclear chemistry does involve all of those things, of course, some of the lesser known things that nuclear chemistry does apply to are also medicine. There's this thing called nuclear pharmacy, or nuclear medicine in general. Very useful for identifying areas in your body that need help with an MRI. You literally inject yourself with radioactive materials to identify those areas. Not only that, but we also generate massive amounts of electricity and power using nuclear chemistry, so that you can enjoy the modern day life of having lights in your home and a freezer and fridge that can store your food for a prolonged period of time, keeping it nice and cool. There are two types of nuclear processes that we're going to talk about. The first is nuclear fusion. In fusion, you basically have two smaller nuclei that fuse together to create a larger one. Now, this is the process that produces the enormous amounts of energy that come from our sun. In the sun's core, you have hydrogen protons that literally fuse together to create helium. That process looks like this. Basically, you have, again, two different hydrogen atoms that are going to come together and release an enormous amount of energy, enough to literally fuel and give light to our entire planet and all life that exists thereon, while releasing a neutron and a helium atom. It's important to note here that this process takes place in the core of the sun, and all of that energy and heat is radiated out from that core and travels across space to give our Earth that light and heat that we need to live. The next nuclear process is called fission. I like to envision fission as billiard balls. So in billiard, you put all of the billiard balls into this triangle looking thing, and then you take one ball and you whack all of the other balls with that one ball. That's essentially what we're doing in fission, except that one white ball you're starting with is literally a neutron. And that neutron is going to bombard a nucleus of another radioactive element and create an unstable center core. Once that target nucleus that it impacted becomes unstable, it's going to break apart into smaller products called fission products, and other neutrons will also be given off. Those neutrons that are given off can, of course, go on farther and bombard other target nuclei to continue the chain reaction indefinitely. Now, this fission process is what we use and what we capture in our nuclear power plants to keep the lights on in your home. Before we can solve for alpha, beta, and neutron radiation, we're going to need to first know the notation of nuclear chemistry. Back in the day, we learned from the periodic table elements that this upper right-hand corner represents the atomic number. And that atomic number is also equal to the number of protons that that element possesses. So in this case, uranium has 92 protons located in its nucleus. Notice that when we look over at the nuclear chemistry arrangement, the 92 is written on the bottom and on the left-hand side of the element symbol U. U, of course, standing for uranium. This is standard procedure, so anytime you see 92 written on the bottom left-hand corner, we know that that must be the atomic number. And therefore, it must also be the number of protons present. How about this bottom number over here from our periodic table tile, the 238? What is that? Where does it come from? That was our average mass of all the isotopes of uranium. Each uranium is going to have a different number of naturally occurring isotopes with varying numbers of neutrons in their nucleus. Because of this, the mass varies ever so slightly, and we have to average all of the naturally occurring uranium atoms out there to get a final mass of 238.03. Notice that in our nuclear chemistry notation, the 238 is written up top in the left-hand corner. So anytime we see this number in the upper left-hand corner in nuclear chemistry, we know that that must be the mass number of that atom. Let's delve into our first type of radiation, called alpha decay. We symbolize alpha decay with this little alpha, or kind of like a little fishy symbol here. We also represent it as a 4/2, or 4/2 He. As we discussed previously, this 4 would represent the mass of helium, and this 2 would represent the atomic number, which is again the number of protons. So why do we represent alpha decay with helium? Well, alpha decay literally happens when you have a radioactive nucleus that emits a helium atom. In other words, it literally emits something with 2 protons, 2 neutrons, and 2 electrons. What do I mean when I say emit? It means it loses that. It's no longer a part of this original radioactive nucleus. And now helium is literally on its own, floating away from the original nucleus it branched out of. Therefore, if we were literally going to try and solve for an alpha decay of an element, like plutonium, for example, we would need to take into account that it is losing 4 from its mass, and it is losing 2 protons as the alpha decay occurs. In order to solve for that, we're literally going to just subtract 4 from the original mass number, and we're going to subtract 2 from the original atomic number. That'll give us a new value of 92 for the atomic number, which is now an entirely different element. It's not plutonium anymore. Since the atomic number is literally linked to the number of protons an element has, if you change the number of protons, you literally change the element. So looking to your periodic table, if you find 92 as the atomic number, you notice that that is uranium. So you literally created uranium from plutonium after alpha decay occurred. Now what's the mass of this uranium? It's going to be 239 minus the 4. That gives us a value of 235. Well, just wait a second. On the previous slide, the mass was not 235 for uranium. In fact, it was 238 on the previous slide. Well, remember, uranium has varying numbers of neutrons, which will inevitably affect the mass. Remember, there are many isotopes of all of the elements, which is just due to the varying number of neutrons present. Again, this does not affect the proton value or the atomic number, only the mass value. Now that you've seen me do an alpha decay problem, go ahead and pause the video here and see if you can solve the alpha decay for neptunium. Ready? Go. Let's check your answer. We successfully created protactinium. Moving on to beta decay. We're going to represent beta decay with this fancy little cursive looking B thing, or we also represent it as follows, a 0 minus 1 with an E for electron. That should give you an idea that beta decay has something to do with electrons. So basically what happens for beta decay is that you have one neutron that has, again, no charge because it's a neutron, and it spontaneously breaks apart into a proton, becomes positively charged, and emits, of course, the electron that would balance that positive charge. This electron is high energy upon its emission. So then how do we solve for beta decay? I'm so glad you asked. Let's take a look at carbon-14. Now, if carbon-14 were to undergo beta decay, what would be the new element that forms? In this case, we know that the proton number or the atomic number is going to be affected. We're literally taking a neutron and we're turning it into a proton. Therefore, this bottom number here, the atomic number or the number of protons, we're going to have to add 1 for every beta decay event that occurs because we've created an additional proton. However, the mass number up top isn't going to change. That's also why this 0 exists up here in our notation. Now, it might be confusing because we have -1 written there as well. You might be tempted to subtract 1 from this atomic number value. Don't do that. Remember, the premise of beta decay is the fact that the neutron converts to a proton. So we are literally adding a proton to the nucleus. In this case, that would then become 7, and 14 will be left alone. If we look to our periodic table to see what element is number 7, we find that to be nitrogen. So if carbon were to undergo beta decay, we would end up with nitrogen. Now that you've seen me try it, go ahead and pause the video here and see if you can solve for the beta decay of nitrogen then. Ready? Go. If that nitrogen atom undergoes beta decay now as well, we're going to still have to add another proton to the proton value down below, leaving the mass number alone. So it would still be 14, but 7 plus 1 because of the extra proton would be 8. So then we would create oxygen. Next up is gamma radiation. Gamma radiation is literally pure energy, and it's represented by this weird upside down squiggly thingy that I always have a hard time drawing. Basically an upside down fish, or a fish standing on its head, I guess? Question mark? Usually this pure energy is emitted after an alpha and a beta event occur, as kind of the leftover energy at the end. There's basically this super unstable nucleus that has all this extra energy that it doesn't know what to do with, so it just gets rid of it. We also consider this energy to be high energy photons emitted from that radioactive nucleus. Now, because gamma radiation is just pure energy, the way we solve for it is literally by doing nothing to the mass or to the atomic number. It's just pure energy given off. So we're going to represent it as the weird upside down fishy symbol plus the same exact mass and proton value that we started with. So nothing will be changed about the actual element given. The only thing we need to indicate is that there was energy released. Last but certainly not least, we also have neutron radiation. As implied, it involves neutrons, the thing that has zero charge. That's also why we represent it with a 0, or with the 1, 0, N for neutron. Neutron radiation can happen both in fusion, that's the process we talked about that happens in the sun's core, where two smaller particles will come together, fuse together to create a larger one, like hydrogens fusing together to form helium, for example. Or neutron radiation could also occur in fission. That's the process we talked about happens in our nuclear power plants. In this case, we would have a radioactive nucleus and we would bombard it with a neutron in order to make it unstable. It would break apart into those larger nuclei and also release other neutrons to react with other radioactive nuclei nearby. So basically, since neutron radiation is the result of either nuclear fusion or nuclear fission, it's just the release of neutrons being able to react with other stuff around it over and over and over again, in a domino effect reaction chain. Because of this, in order to calculate for neutron radiation, we need to take a look at whether or not the neutron is coming in to the radioactive nucleus, or is it leaving radioactive nucleus? In which case, we would add 1 to the mass. It does not affect the proton value, so we'll leave that bottom left-hand corner number alone and only add or subtract from the top corner number. Or if it's leaving the radioactive nucleus, we would subtract 1 from the mass. Again, that upper corner number, and leaving the atomic number alone. For example, let's say hydrogen was bombarded with a neutron. In this case, we would be adding 1 to the mass number, but the atomic number, hydrogen, will still stay the same. It's not affected. The only thing that's changed is that we gained more mass by adding an extra neutron, so we would make that 2 instead. But now if that hydrogen atom became unstable and released a neutron, then we would need to subtract 1 from the mass yet again to yield a hydrogen with a mass of 1 and still a proton number of 1. So the moral of the story here for neutron radiation calculations is it depends whether or not the neutron is coming in and bombarding, or whether the neutron is leaving and subtracting from the mass number. Let's take a look at this picture over here. We see that the neutron radiation, indicated in red, passes through paper, passes through thin metal such as aluminum, passes through an entire lead block wall, but the one thing that stops it is water. This is the reason why, when we're looking at a nuclear reactor, that the uranium rods used in the nuclear fission process are literally submerged in water. This way, as the neutron radiation occurs, in other words, neutron bombardment into the uranium atoms on the rods, we can control the rate at which this neutron radiation occurs by keeping it submerged in the water. Now that you know about alpha, beta, gamma, and neutron radiation, go ahead and pause the video here and see if you can solve for these nuclear decays. Ready? Go! Let's check your answers. For the first one, we know that it's undergoing beta decay, based off of the symbol provided. And since it's undergoing beta decay, we know that that means that there's a neutron that's literally turned into a proton, releasing a high energy electron. Since we have a neutron turning into a proton, we know the mass will remain unaffected, so we're not going to do anything to that mass number. Keep it at 42, the meaning of life. Obviously, we can't change that. But the one thing we are going to change is the fact that we added a proton, so we are changing this atomic number by adding 1 to it. Again, don't be confused by the notation being -1. We are adding 1 to that atomic number for a final number of 20. And if we pull out our nifty-difty periodic table, we can see that number 20 is calcium. So when potassium undergoes beta decay, we create calcium. How about that second one? When we compare our beryllium over here to our beryllium on the product side, we see nothing has changed. Therefore, the decay that's implied here must be our gamma. In other words, just high energy release, or high energy photons, if you will. And lastly, we see uranium is undergoing some kind of decay. What decay is it? Let's take a look at what the product is. We have 231 and 90 from 235 and 92. That certainly looks like we lost 2 from the 92 over here to get 90 here, and we lost 4 from 235 to get to 231 over here. That certainly looks like a helium atom was emitted. In other words, alpha decay was the culprit here. Now the next question you might be asking yourself is, well, which one is the deadliest? Which one is the scariest? Let's take a look at the following depiction. In alpha radiation, that's our helium nucleus right there, we notice that a piece of paper can stop it. So literally just holding up a piece of flimsy paper, whatcha! And I just stopped the alpha particle from hitting me. However, if I say had my mouth open and ate the helium particle, the alpha particle, it would have nowhere else to go. It would be bouncing around inside my body, so that would be pretty bad. Therefore, alpha particles, in terms of just hitting you if you were to be blasted with them, not so scary. However, if alpha particles were to, say, fall all over our crops and enter our water system, and then we were to ingest those, big problem. How about the beta radiation then? Beta we see here as our high energy electron, or the neutron getting converted to the proton, goes right through the paper and can be stopped by a sheet of aluminum. So if we were wearing proper safety gear in terms of being exposed to beta radiation, we should be okay for the most part. And if we were to ingest it, it is small enough to hopefully also exit our body and not do too much damage. Although I'd really rather not be bombarded with alpha or beta particles at this point. And lastly, let's check out gamma. Gamma is just our high energy. We see it passes through paper, aluminum, and in some cases also a block of lead. So in terms of just being directly exposed to it, I would probably say that gamma is not our friend. Alright, let's take another stab at some practice. Go ahead and pause the video here and see if you can show the beta decay of promethium-146. Ready? Go! Let's see if you were able to figure out this notation and also apply beta decay. And there you have it. If promethium undergoes beta decay, you should end up with samarium. Okay, here's your last practice problem, I promise. Go ahead and pause the video here and see if you can solve for the alpha decay of radon-198, now that you know what that notation means. Ready? Go! Let's go ahead and solve that alpha decay of the chemical that causes 21,000 cancer deaths per year, equivalent to 58 deaths per day. If radon went through alpha decay, we would end up with polonium. In this lesson, we discussed the various types of nuclear reactions that take place. The first being nuclear fusion. That's where you have two separate nuclei that fuse together to form one larger one. This is the process that happens in the sun's core. We also talked about nuclear fission. That's when you have a nucleus that's bombarded with a neutron. That causes the fission to take place because this now becomes unstable and breaks apart from one nucleus into two separate nuclei, also releasing multiple other neutrons that can go forth and bombard other nuclei, which is the process that occurs in nuclear reactors, the things that keep the lights on in our home. We also discussed alpha decay, which is basically just the release of a helium nucleus, calculated by subtracting 4 from the mass and 2 from the atomic number, which is equivalent to the number of protons present. Then we moved on to beta decay, which is just a neutron turning into a proton, also emitting a high-energy electron. Since we convert a neutron to a proton, that means we're going to leave the mass number alone, and we're going to add 1 to the proton value, or the atomic number. Gamma radiation is just really high energy leftover radiation from the alpha and beta decays, typically. So we're only going to show that by drawing the upside down weird fishy symbol thing without any other further calculations necessary to the element given. And lastly, we talked about neutron radiation. This is the result of either fission or fusion, and we have to take into account whether the neutron is coming in to calculate by adding 1 to the mass number and leaving the proton number alone, or if the neutron is exiting out of the nucleus to bombard other nuclei. If it's leaving, we would have to subtract 1 from the mass number, leaving the proton number or atomic number alone. Now that you know those basics of nuclear chemistry, see if you can solve for the nuclear disintegrations or decay of the unstable isotope of uranium, U-238. If you'd like to know if you got this answer right, stick around to part 2 of this series in nuclear power to see the answer to this question. Please give this video a giant quacks up, and be sure to undergo some fusion with the Kanta by subscribing to the channel. Quack you later.
No ducks, no glory.